bang, giving birth to an endless expanding existence of time, space, and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. They appear out of nowhere and threaten our very existence. From rocks crashing through homes to Mount Everest-sized boulders triggering mass annihilation, no one is safe from their wrath. And some of these intruders are not extraterrestrial. They're actually man-made cosmic junk. Take cover as we investigate meteorites and space debris, the deadly stuff that falls from space. "11:39 p.m., October 6th, 2008. The Catalina Sky Observatory in Arizona notices something it hadn't seen before. An asteroid the size of an SUV is screaming down towards Earth at over 27,000 miles per hour. An alarm sounds throughout the international scientific community. Is this asteroid on a collision course with Earth?
This object was special because it was probably going to impact the Earth. And over the course of the next 21 hours, 500 observations were made of the object to try to exactly calculate its orbit.
At NASA's Jet Propulsion Laboratory, Steve Chesley gets the urgent wake-up call. Everyone wants to know when and where this rock will touch ground.
They sent me the data. I rushed into the office rather excitedly and spent the next couple of hours trying to get my arms around the problem and running the numbers. And I reached the conclusion it was a 100% chance of impact.
Chesley calculates the collision will occur in less than 13 hours, approximately 5:45 a.m. Eastern African time. Its target, the Nubian Desert in northern Sudan.
We had really expected or anticipated the discovery of an asteroid that was going to hit the Earth before impact. With time to react and time to predict the location of the impact, it was very extraordinary. Never seen it before.
It was countdown to impact.
Steve Chesley.
With no time to stop this runaway space rock, emails went out to alert those on the ground and in the air. 5:45 a.m. The moment has arrived. A commercial pilot is flying over Sudan. He witnesses a fireball smack right into the Earth's atmosphere with the energy of about 1,000 tons of TNT.
As it entered the atmosphere, it started to burn and brighten. At some point, the stresses on the body became so fantastic from the atmospheric pressure that it just exploded. That explosion would have sounded like a sonic boom.
On the ground, 23 miles below, Sudanese people returning from morning prayers hear the frightening sonic roar. Witnesses see a brilliant fireball, followed by mysterious flashes of light streak across the sky. Scientists had hoped the asteroid wasn't heavy enough to completely penetrate through the Earth's atmosphere and wreak havoc on the ground. Satellites track the fiery explosion, but there is little indication that any fragments survive.
So there is a possibility that people could be frightened by such an event, but the risk of injury is really very low from something so small.
And Steve was correct. There were no reports of injuries or damage due to falling debris in the remote region. Planet Earth was spared from a potential disaster, partly because the region was so remote and the impactor was small. But the story doesn't end here. December 2008. Astronomer Peter Yeniskis organizes a search and recovery team from the University of Khartoum in Sudan. He's determined to find the unlikely. Meteorites, the surviving fragments of the asteroid named 2008 TC3.
We had a busload with students who were all eager to go and search. We drove 29 kilometers into the desert to go to the area close to the explosion to look for the smaller pieces that might have survived.
The meteorite hunter's only guide is a map of the Nubian desert with the projected approach path of the asteroid.
They basically used my trajectory and the ground track that I had laid out on the desert floor as a guide for their search.
Lined up everybody about 20, 30 yards apart, and then started walking down the desert in line, searching for things that were black.
But spotting small charcoal-like stones on the rocky desert surface is akin to finding a needle in a haystack. As the sun begins to set on the first day, the team is about to walk away empty-handed when a student suddenly comes forward with a suspicious rock.
A student called Mohammed Alamin had this little rock in his hand that was clearly a meteorite. It had a beautiful black fusion crust around it, and it was undoubtedly a meteorite. And then everybody started being excited and shouting and singing and waving their hands.
280 meteorite samples were eventually recovered, equaling 11 pounds, which for planetary scientists was like hitting pay dirt.
This was one of the meteorites that was recovered. Not much bigger than this. We think that a lot of these meteorites, when they came out of the explosion, were tumbling very rapidly, and that resulted in breaking of the meteorites when it was still up in the air.
2008 TC3 is the first asteroid ever observed in space, which was later found on the ground. Scientists are calling it the first asteroid sample return mission.
It's the first time that we've actually detected something in space, figured out that it was going to hit the Earth, figured out where it was going to hit the Earth, and we actually saw it hit the Earth. We've even recovered pieces of it. That's remarkable.
This whole experience was really fantastic for us. This was an excellent test for what we're really preparing for, which is the possibility of having to deal with a larger impactor sometime in the future.
Planet Earth may not be so lucky the next time. Scientists now suspect 2008 TC3 came from a piece of a much larger rock from the asteroid belt, a region between Jupiter and Mars where asteroids and comets take up residence. In this crowded galactic neighborhood, these fossil relics from the formation of the solar system occasionally collide with each other and explode into smaller pieces. It's these fragments that can migrate towards Earth.
A bullet can provide a pretty good stand-in for one asteroid striking another in terms of its impact speed. Asteroids in the main asteroid belt will run into each other at speeds of over 11,000 miles per hour. Now, a bullet traveling out of a rifle can be a good analogy for that because they will leave a rifle barrel at speeds, maybe a fifth that. So it doesn't just fragment. It literally blows itself to pieces. Okay, we'll head downrange and actually set up our little artificial asteroids at a safe enough distance to shoot. Since real asteroids are hard to come by, we're going to use a couple of stand-ins today.
These bullet impacts are comparable to the collisions in the asteroid belt.
Let's see what our results are here. This is actually rather typical of the results of an asteroid impact, where you tend to have a few large pieces of debris, several medium-sized pieces, but nature is very good at making lots and lots of little debris. These little kilometer-sized fragments are what we actually see today as the near-Earth asteroids, these fragments which have worked their way in from the main asteroid belt, approaching the inner solar system, passing near our planet, sometimes impacting our planet.
These near-Earth objects, or NEOs, have transformed our near-space environment into a danger zone.
The speeds with which objects are running around in the inner solar system is it's much akin to actually a bunch of cars driving crazily down a highway. The vehicles themselves are traveling at high speeds. When they cross lanes without looking and perhaps running into each other, they are hitting at equally high speeds. And that's kind of like objects moving on their own independent orbits around the sun.
Every few hundred years, Earth gets hit with rocks the size of a football field that can destroy entire cities. But every 500,000 years, we get struck with boulders the size of mountains that could ignite global disasters. The Earth's atmosphere, a layer of gases surrounding our planet, incinerates most material. But occasionally, larger, heavier objects slip through.
As soon as they enter the Earth's atmosphere, they get slowed down, decelerated by the atmosphere, and they lose pretty much all of the velocity with which they entered. And during that time is when you see the fireball event. But once they lose that velocity that they came in with, they essentially just fall pretty much at terminal velocity onto the Earth's surface.
When asteroids hit the Earth's atmosphere, they become meteors, bright fireballs in the sky. If they make it to the ground, they're called meteorites. Over the past century alone, meteorites have struck homes, vehicles, and even people. In 1954, an 8-pound meteorite crashed through the roof of a home in Sylacauga, Alabama, and hit a woman in the hip, leaving her with nasty bruises. In October 1992, amateur videos caught a fireball flashing across the skies above several Atlantic states. The 27-pound meteorite eventually crushed the back end of a car in Peekskill, New York. In November 2008, a police dash camera recorded a bright meteorite explosion in the skies over Alberta, Canada. These caught-on-video impacts prove that things really do fall from the sky. What's even more startling is the physical evidence of much bigger impacts, ones that have caused global catastrophes in the past and may ignite a cosmic Armageddon in the future. Earth was not always an ideal address for human beings. During its infancy, 3.8 billion years ago, the third rock from the sun was a cosmic war zone. During this brief period, called the Late Heavy Bombardment, billions of leftover debris from the formation of the solar system pummeled our planet at rates up to 20,000 times higher than today.
What happened is that Jupiter and Saturn, the two giant planets in our solar system, went into what's called a gravitational resonance with one another. So Jupiter made 2 complete orbits around the sun for every single orbit made by Saturn. And when that happened, it rearranged the entire solar system. It reshuffled Uranus, Neptune, Jupiter, and Saturn, and moved the giant planets farther out. When that happened, that just sent a volley of comets and asteroids rocketing into the inner solar system.
At the same time, these rocky bodies helped to mold our baby planet to the shape it is today. Here are the battle scars. Only 170 impact craters are still visible on Earth. Weather, water, and plate tectonics have erased most traces of ancient cosmic violence. But proof of Earth's tumultuous past lies on the Moon. which was formed at the same time, but lacks plate tectonics and other erosion processes that tend to erase the evidence.
The Earth itself has been bombarded every bit as much as our nearby moon. If you look up at the moon in the sky and you see its cratered surface, you have to imagine our own Earth cratered and battered to at least that degree, and in fact, because we're a bigger target in space, even more.
By counting craters on the moon, scientists can learn about the number of impacts on the nearby Earth, past and present.
Scientists can learn about the sizes and compositions of asteroids that impact the Earth by studying the characteristics of the craters that they create. So we're going to try and demonstrate that today by tossing some weights into the sand on the beach here, and we're going to see if we can come up with a relationship between the size of the weight and the size of the crater that it creates. Based on my measurements, I calculate that this beach was impacted by 3 rocks, 10 inches in diameter, 5 rocks that were 6 inches in diameter, and 11 2-inch diameter rocks. This technique of measuring the size and frequency of craters on this beach is very similar to the technique that scientists use to understand the frequency of impacts throughout Earth's history.
Today, the best preserved impact craters exist in dry desert regions around the world. Meteor Crater, located near Winslow, Arizona, is one of the lasting reminders of the destruction caused by objects from space. And scientists are just cracking the surface of understanding the repercussions of these ferocious events.
Okay, lights.
Okay, do we want to back one off to 250,000?
Planetary geologist Pete Schultz formulated a new experiment to simulate what impact craters look like under the surface.
1.1 feet.
At the Vertical Gun Range at NASA's Ames Research Center, Schultz is using a massive 30 caliber light gas gun that shoots projectiles at various targets inside a vacuum chamber.
Today, we're going to try to look inside a crater as it forms. And to do this, we're going to use a clear block. It's transparent, so we actually get to watch the crater as it grows, but from the inside rather than from the outside. This little bead is simulating an asteroid that's going to slam into the surface of the Earth. So let's get inside. We're in the impact chamber. This is where everything happens. The little projectile bead is going to be coming in at around 4 miles per second. We're going to hammer this transparent block. We're going to be looking at everything that happens below the ground when an asteroid hits the surface of the Earth.
Outside the chamber, high-speed cameras will document the deep impact from various angles.
Are the Shimatsus all up down there?
In the control room, Schultz watches the monitor with nervous anticipation.
High voltage?
The vertical gun launches the glass bead projectile into the acrylic block.
Sweet. Wow, okay, that is just frickin' gorgeous.
The experiment was a smashing success.
Kapow! So here we actually have the impact, but now we see this vapor plume. This is really hot gas. It's about a temperature close to the surface of the sun. And then as it moves away, it cools, and now we begin to form the crater with the ejecta coming out. And now we're watching the crater actually begin to form on the inside. That is awesome. Okay, I want to see what we did. Oh man, did we bust this up. Now we can look to see how these cracks develop through time. So if this were a big impact, these cracks would grow where the entire crater could then collapse inward and fail.
Impact experiments at the vertical gun range shed light on the large-scale destruction caused by asteroids that have fallen from space.
When we see an impact, it's not just the cracks and cracking. You will also see the vapor plume expanding. That affects life. That affects survival. If this impact occurred on Earth and was large in scale, it would simply fry the atmosphere. It would send debris out, and as it hits the Earth, again, it would cause more devastation.
Scientists have discovered that impacts from space have affected the evolution of life on Earth.
We know that, in fact, the flux of meteorites hitting the Earth was much higher in the past than it is today. And in fact, there have been known instances, for example, the large impact event 65 million years ago at the Cretaceous-Tertiary boundary.
$65 million years ago, an asteroid the size of Mount Everest struck the Yucatan Peninsula in Mexico with the energy of a 100 million megaton bomb. It created a 100-mile wide crater underwater that was finally discovered in the 1980s. Scientists have determined that the asteroid impact ignited atmospheric events that may have led to the mass extinction of 75% of all prehistoric species, including the dinosaurs.
There were a lot of potential effects that could have led to the extinctions. Heating of the atmosphere, for instance, by the ejecta, perhaps leading to wildfires. The poisoning of the atmosphere from the gases produced from the vaporized asteroid. It was every ecological disaster you could think of all happening at the same time.
But was this the last time an asteroid triggered a mass extinction? A controversial new theory suggests a space rock was responsible for the disappearance of the Ice Age megamammals of North America. Scientists are dying to know what happened 13,000 years ago. The Ice Age was slowly ending. The North American continent was inhabited with big beasts like the woolly mammoth, mastodon, giant ground sloth, and the short-faced bear. But something caused 35 major groupings of species to vanish from the fossil record. Many think the ancient Clovis people, a hunter and gatherer society, killed off the mega mammals. But startling new evidence suggests that an object from space may have led to the demise of the giant creatures.
13,000 years ago, the climate changed suddenly, rapidly, and dramatically. It looks like there was some type of extraterrestrial event, whether it was a large meteorite, an asteroid, or a comet exploding in the atmosphere. And all of a sudden, the planet was thrown back into a little ice age.
North America experienced a brief return to Ice Age conditions. So could there be a connection between this cold snap and the disappearance of the mega mammals? Archaeologist Ken Tankersley claims to have dug up evidence of a possible cosmic impact in Sheridan Cave, located in Cary, Ohio.
And I'll see what you found so far.
It's one of only 12 known sites that have been precisely dated to the time of the late Pleistocene extinction, which was the end of the last ice age. In this deep cavern, Tankersley and his team have discovered the burned remains of more than 60 species of plants and animals from that time period, including hunting weapons of the Clovis culture.
I don't believe it. This is a Clovis bone point. It's manufactured from a megamammal rib, probably a large animal such as the American mastodon. What's fascinating about this specimen is the person who manufactured this likely witnessed the event 13,000 years ago.
Tankersley says that most of the bones he's uncovered underwent intense burning that couldn't have been caused by a mere forest fire. He says it had to have been from a colossal explosion, the kind generated by an Earth impact. And the archaeologist says he's found the smoking gun.
Oh, look what we have here.
It's hidden in a dark geological layer of dirt called the Black Mat, which dates back to 12,900 years ago. This layer has been uncovered in more than 50 locations in North America.
Note this black area. Let's see if I can trowel through here and bring out some of the more dark areas. Oh, nice. We're literally at this spot looking at the contact of the end of the last ice age. And this oxidized layer above it, this is where the megamammals go extinct.
Within this sediment layer, some scientists claim to have found key pieces of evidence that point to a cosmic impact. Carbon spherules created by intense fires. Shocked diamonds formed through extreme temperatures and pressures. Lonsdale-ites, rare hexagonal-shaped diamonds that are only found in meteorites. And micrometeorites, minuscule pieces of iron and nickel that come from outer space.
If we take a magnet and run it across this oxidized layer, my guess is we'll probably pick up micrometeorites. You can see how the sediment's adhering. And just as the magnet picks up iron from this layer, so does the magnet adhere to this meteorite. And this suggests, because we have a high concentration of micrometeorites in this layer and a complete absence above or below, and it's at the event of 13,000 years ago, something dramatic occurred here.
We know that all over North America there is a thin layer of dust and particles just before that black mat formed. That indicates that something happened right before the event. That is the climatic change. What is it? We still don't know exactly. All we know that something happened.
To date, no impact crater has been found. But a space rock doesn't have to reach the ground to generate mass devastation. In 1908, a rocky body slammed into the atmosphere 6 miles above Siberia's Tunguska wilderness. It released energy yielding about 5 megatons of TNT.
You can imagine what it feels like to do a belly flop off of a high diving board and you smack into the water. A small, weak, rocky asteroid will kind of undergo a similar sort of feeling as it very quickly is decelerated and braked in the dense lower atmosphere.
Immediately after the Tunguska airburst impact, an intense shock wave and hot air blast traveled to the ground and spread outward. It engulfed almost 1,000 square miles of forest. Some scientists propose that a similar scenario may have contributed to the extinction of the North American megamammals. And a comet, not an asteroid, may have been the culprit. Unlike asteroids, these dirty snowballs contain more ices and gases that tend to break up before reaching the surface.
When the theorized comet came down into the Earth and would have exploded in the atmosphere, it would have distributed amongst the ejecta that was created beneath it. It would also have seen a great variation in the deposits left behind. There would have been intense burning over a large area. Anything within the impact zone, of course, would have been devastating. At the same time, however, it would not have had immediate impact for the rest of the planet.
just within the impact area itself.
This so-called Clovis comet theory suggests that profound climate changes led to the eventual extinction of the mammoths from North America. However, contrary to popular belief, a small number actually survived in various regions of the world up until around 2000 BC. And archaeological evidence indicates that the Clovis culture didn't go extinct from this alleged impact. Rather, they adapted to their changing environment.
When the large game animals that Clovis people were hunting disappeared from the landscape, people had to change the way in which they were hunting and gathering.
We may never know with certainty whether a near-Earth comet caused the Clovis event. But would modern man learn to survive after an Earth impact? We may eventually be put to the test. At this very moment, meteorite scientists scour the landscape in search of these messengers from the sky. These space rocks hold clues to impacts of the past, and as scientists are now discovering, clues to what is coming in the future. Mass extinctions, mile-wide craters, scorched landscapes, all created by objects from space. Meteorites have been intruding on our planet since the formation of the solar system. So where do we typically find these rocks?
Most meteorites, they're more easily found in dry desert regions of the Earth, for example, in the Saharan desert or even the cold deserts like Antarctica, where there's not a whole lot of vegetation or there's not a whole lot of other rocks to confuse you. However, meteorites fall everywhere on Earth with equal probability.
Cosmochemist Meenakshi Wadhwa has traveled the world in search of meteorites and now oversees the largest university-based meteorite collection in the world.
We're here looking at the collection of meteorites in the Center for Meteorite Studies at Arizona State University. There's basically 3 different kinds of meteorites. You can have stony meteorites, stony iron, or iron-rich meteorites, but all 3 kinds have at least some amount of metal. And so you can distinguish terrestrial rocks from meteorites by the content of metal in meteorites. The other way to actually distinguish a meteorite from a terrestrial rock is that you'll actually see a fusion crust on meteorites that forms on these objects when they're falling through the Earth's atmosphere.
Most of the meteorites recovered originated in the asteroid belt between Jupiter and Mars. But nearly 4 dozen actually came from our moon and the planet Mars.
The idea there is that you probably had a large asteroidal body that impacted the moon or Mars and ejected pieces of the crust of the moon or Mars. And these ejected pieces probably fell into these unstable Earth-crossing orbits, and eventually pieces made their way to the Earth that way. This is a piece of a lunar meteorite, and we believe it came from the Highlands portion of the moon. And we know that this is actually a lunar meteorite because we can compare this with actual samples that were brought back by the Apollo missions in the late 60s and early 70s.
Meteorites are precious research subjects. Although they've destroyed life time and time again, they may also have provided the chemicals needed for life on Earth.
This is possibly one of the most well-studied meteorites in the world. It fell in 1969 in Mexico. And an interesting thing to note about this rock is that these white grains are possibly some of the oldest solids that formed in our solar system as our solar system was forming 4.5 billion years ago.
These white grains, combined with the atmospheric chemicals and organic compounds on Earth, may have formed a mixture of amino acids, the essential elements of life.
So meteorites have played a very important role in possibly the formation of life on our planet and certainly the evolution of life on our planet.
Meteorites may have once provided the necessary components for living things. But they can be a source of grave concern when they hurtle down from space without prior warning. September 19th, 2007. A fiery meteorite streaked down from the sky and impacted the soft soil near the Peruvian town of Caracas, which borders Bolivia. Debris flew over 600 feet as the meteorite left a crater over 15 yards wide and 15 feet deep.
There was a gentleman riding a bicycle, and he was knocked over. Another person looking the other direction quickly turned around and saw this thing hit with a large plume rising above. In talking with the locals, the villagers, they had no idea, except they thought maybe this was some form of military action. You know, they're very close to the border of Bolivia.
Scientists reassured the locals that a meteorite, and not a missile, caused the impact crater. But immediately after the event, many villagers complained about headaches and vomiting.
They literally became ill, most likely because of sulfur or because of the fine dust that was inhaled. The vapors probably came from the material that was following the meteorite as it was coming through. It was melting, it was vaporizing as it passed through the atmosphere, and it probably, when it hit, caused some additional release of gas.
But could a space rock actually deliver harmful elements to Earth? Sci-fi movies and conspiracy theorists have proposed that meteorites could seed our planet with lethal bacteria or viruses. But what's fact and what's fiction?
The probability of this happening is very, very, very small. If that rock made it to Earth and somehow that microbial life form survived, it would find our atmosphere very toxic. Any microbe that evolved in an anaerobic, in a non-oxygen environment, is not going to survive long in oxygen.
The possibility that the Peruvian meteorite committed cosmic biological warfare is remote. But had this small stony meteorite impacted a nearby village, the aftermath would have been much different.
This would look like somebody had planted a roadside bomb. It would have had that effect. It opened up a hole so large that it would have swallowed several cars.
The Peruvian meteorite impact once again illustrates the unpredictability of things that fall from the heavens. And space rocks aren't the only objects that can cause bodily harm. Up to 200 heavy objects hit our planet each year. And they're not extraterrestrial, they're man-made.
By GNC.
2 minutes to
February 1st, 2003. The space shuttle Columbia was about to conclude its mission in space when disaster struck. The vehicle disintegrated during re-entry into Earth's atmosphere. Debris fell over Texas, Louisiana, and Arkansas. All 7 crew members perished.
Because of reentry heating, it got hotter as it came into the atmosphere. Some critical components failed. That caused an overall failure of the entire spacecraft, which spread debris over a large footprint.
Spacecraft re-entry disasters are rare, but space debris is not. Since the beginning of the space age, rockets have carried thousands of satellites into orbits around our planet. As a result, we've littered space with spent rocket stages, defunct satellites, fuel tanks, as well as nuts, bolts, and fragments from collisions and explosions with other debris. This abandoned space debris hovers over our planet like a cosmic garbage dump, and some will eventually fall back to the Earth. The question is when and where.
Things that re-enter the atmosphere, they do have a risk. The real risk is that something falling through the atmosphere will hit a person on the ground.
5,400 tons of space junk has already crash-landed on Earth. In 1979, Skylab, the first space station, scattered debris across the Indian Ocean and parts of Australia. In 1997, a DVD-sized piece of smoldering metal fell from the clouds and brushed the shoulder of a woman near Tulsa, Oklahoma. She wasn't injured, but hundreds of miles away, this 570-pound stainless steel tank landed next to a farmer's house in Texas. Both were pieces of debris from the same stage of a Delta II rocket.
It's a piece of debris from a launch stage that was in orbit for about 9 months and re-entered over the northern part of the United States and Canada. Came down and left several fragments of debris around. This was the largest piece.
At the Aerospace Corporation in El Segundo, California, scientists study space debris to find out what materials survive re-entry and why, and how to minimize future hazards.
This is remnants of a stage that put a GPS satellite into orbit. This was found in Saudi Arabia. This one is made out of titanium, which is a very high melting point material, and that's one reason why this one survived so nicely. And this was traveling again on the order of probably 150 miles an hour when it hit the ground.
Why do objects fall back to Earth? Most space debris resides in low Earth orbit, approximately 600 miles above our planet's surface. In space, objects can stay for tens to hundreds of years because there's no air resistance. But they will eventually undergo orbital decay. They will lose energy because there's very little atmospheric drag, and the Earth's gravity will tug them back down into its atmosphere.
Satellites fall back sometimes quickly and sometimes over a long period simply because they begin to touch a little bit of the atmosphere, enough of the atmosphere that there's an increasing force over a long period of time, and that small force acting over a long time will basically drag them out of orbit, and they will eventually re-enter.
Most debris burns up during atmospheric re-entry and vaporizes. However, some pieces are made of stronger components such as stainless steel and titanium, which can survive tremendous heat. Once below the dense regions of the atmosphere, they literally free fall to the ground.
It'll hit at a very low velocity, say 150 feet per second or 150 miles an hour, something like that. And so that's the problem. So you're basically slowing something from an orbital speed down to essentially nothing in a relatively short time.
Main engine start.
The international space community now imposes new design requirements for most objects, including a propellant system to ensure controlled re-entries over water.
Basically, the international community has agreed that an acceptable level of risk for a reentry is around 1 in 10,000. That means that if you did a particular reentry 10,000 times, the likelihood is that you'll hit one person on the planet. And so if you exceed that threshold, the objective is that you should reenter that piece of hardware into a safe area like the ocean.
But new guidelines won't have any effect on the thousands of pieces of old debris already in space.
Unfortunately, we have a number of objects in space still which were not designed when that requirement was around, and they still are slowly coming down. So it'll be a while before some of these things take effect.
It's no longer a sci-fi fantasy. Extraterrestrial and man-made things continue to fall to Earth. We constantly need to search the skies for objects that could decimate a neighborhood, or even worse, end human civilization. In the beginning, there was darkness, and then bang, giving birth to an endless expanding existence of time, space, and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. asteroid impacts that rain death from the sky. Entire planets colliding and turning worlds into dust. A black hole that's been blowing away the rest of its galaxy for 100 million years. And massive stars that rock the universe like nothing else. Get ready to be blown away in a countdown of 10 of the largest explosions in the cosmos. These are the biggest blasts in the universe. They can not only wipe out cities filled with millions of people in the blink of an eye, but can lay waste to entire continents, planets, and even rip galaxies apart.
The universe is filled with tremendously violent explosions and blasts and events. The calm serenity of life on Earth is, to some degree, the exception, not the norm.
And whether they're massive collisions or explosions of entire stars, they all have important elements in common.
Really, another way to say explosion or blast is just a big liberation of energy all at once. When you liberate a lot of energy in something that already has structure, you tend to demolish the structure, so it seems very destructive. But the laws of nature will take energy and reconstruct it into some other form.
In 1994, more than 20 pieces of the Shoemaker-Levy 9 comet pummeled Jupiter.
There were big black scars all across the face of Jupiter, so large even that they could be seen clearly even with amateur telescopes.
The largest comet fragment was more than a mile wide, and the force of its impact was equal to 6 million megatons of TNT.
That's about 100 times or more of the entire nuclear arsenal of the world. So if you took every bomb in every corner on Earth and exploded it in one big explosion, you wouldn't even begin to touch the power of this fragment colliding into Jupiter.
But guess what? Even that type of power isn't enough to qualify as one of the biggest blasts in the universe. The first event to make the top 10 was many times more devastating. Number 10, death from the sky. The smallest blast on our list may still have been big enough to wipe out the dinosaurs by blocking out the sun with smoke and debris. It's the Chicxulub impact, the asteroid that crashed into Mexico's Yucatan Peninsula about 65 million years ago. A 6-mile-wide space rock, taller than Mount Everest and almost as wide, thundered into Earth.
So I'm sitting in front of the meteor crater in Arizona, and this is about 3/4 of a mile wide. So if we were to drive across this at about 55 or 60 miles per hour, it would take like a minute. Well, the crater created by the asteroid that impacted the Yucatan Peninsula, it would take over 2 hours to drive it at about the same speed. So you can imagine how much larger that crater is than this one behind me.
The 112-mile diameter crater is big enough to fit New York City, Philadelphia, and everything in between inside. If it struck today, about 12 million people would be killed instantly, not to mention the damage and casualties that would spread beyond the crater. That's because the energy in every blast is released in several ways, such as light during the blinding flash of the impact, and heat, capable of spreading wildfires across much of the globe, But with collisions, most of the devastation comes from the energy of motion, known as kinetic energy, which creates the crater and the flying debris.
The energy in the impact that created the crater at Chicxulub had to have been enormous, probably about 250 million megatons. That's a lot of energy. The largest bomb ever exploded on Earth was 50 megatons. So that compared to 250 million gives you a sense.
It was also about 40 times greater than the energy released by the largest Shoemaker-Levy 9 comet fragment to hit Jupiter. And figuring out the kinetic energy released in a huge asteroid impact is all a matter of plugging some very big numbers into a simple equation.
The key thing to keep in mind when considering the energy in these kinds of collisions is that the formula for what's called the kinetic energy, the energy of motion, is a half mv squared. The mass, and then the square of the velocities.
Mass is the weight of the object, and velocity is the speed it's traveling.
You can have a huge amount of energy for a massive enough or fast enough object.
Considering that the Chicxulub asteroid weighed nearly as much as Mount Everest and was moving at over 50,000 miles an hour, about 50 times faster than a bullet from a revolver, it's no wonder it was one of the biggest blasts in the universe. But what about its effect on the structure of the entire planet? An explosives expert places a small charge just under the skin of a watermelon to simulate the type of energy released when this asteroid slammed into Earth.
As you can see, something that would be devastating to us is not too devastating to the planet as a whole.
So there's still plenty of room for the blasts to get bigger. Number 9, Martian impact. Luckily, Mars, and not Earth, was the target of an asteroid 200 times larger than the one that slammed into the Yucatan Peninsula.
The asteroid that impacted Mars about 3.9 billion years ago was 1,200 miles wide. Now, that's about the size of Pluto. And if you imagine most of the continental US, from Denver to the Florida Panhandle and Chicago down to the south of Texas, huge.
And that's just the size of the asteroid. The crater, known as the Borealis Basin, is another story. The hole covers about 40% of the planet.
So the Borealis Basin on Mars is about 5,300 miles wide. Now the crater behind me is not even a mile wide. So you can imagine multiplying this by over 5,000 times, and that's the size of the impact crater on Mars. That's about the size of the continent of Africa. Amazingly huge.
While the speed of the asteroid that smacked Mars wasn't much different than the one that hit the Yucatan Peninsula, the mass was many times greater, leading to a much larger release of energy.
Probably about 1 million times more energetic. So it would be about 250 million megatons of energy. And that's a lot of energy. And that's why you got such a big, big basin.
Something like that hitting Earth today would put the instant death toll in the billions and would probably wipe out all life on the planet soon after. But the next blast did blow an even bigger chunk of crust off our planet, luckily before life even existed here. Number 8. The Big Splat. Instead of Mars being a target, imagine an asteroid the size of Mars slamming into Earth. Most planetary scientists believe that's exactly what happened soon after the Earth formed about 4.6 billion years ago. It's known as the giant impactor theory, also nicknamed the Big Splat.
The early solar system was a much busier place than it is today. Basically, it hadn't settled down yet. So there are lots of fragments running around, producing all sorts of collisions, which ultimately produced the bodies we know today.
Earth was still a molten wasteland, devoid of life back then, which is a good thing, since the force of that collision would have ended life in its tracks. So how did the planet recover from the most violent event in its history? Many of the biggest blasts in the universe are caused by comets and asteroids slamming into planets. These impacts can unleash hundreds of times more energy than the entire nuclear arsenal on Earth. But number 8 on our list is even more powerful than that. A blast caused by a rock the size of a planet slamming into Earth. It actually happened soon after the Earth had formed, about 4.6 billion years ago, when an object the size of Mars, sometimes known as Theia, slammed into our world with catastrophic effects. Compared to the Pluto-sized asteroid that smashed into Mars, the Mars-sized rock that nailed Earth was more than 3 times larger, releasing much more kinetic energy.
The Theia impactor that knocked off the crust of Earth was probably about 10 times more powerful than the Borealis Basin impactor.
But this incredibly destructive force also had some very important benefits.
So when Theia impacted the Earth, it happened probably at a glancing blow. And in doing so, the iron cores of the 2 planets actually melded together and formed a larger iron core and a larger Earth. Now, Theia's mantle probably got completely blown off in this impact because it's a little smaller than Earth, and some of the Earth's mantle got blown off. So you have all this mantle debris floating around, orbiting, and it actually coalesced to form the Moon.
The Moon stabilized Earth's axis, preventing it from tilting wildly, which keeps Earth's climate steady. It also slowed Earth's rotation over time to the 24-hour days we have now. Once again, to simulate the power of this blast, an explosives expert places a charge on a melon representing Earth. Could this be the one that blows the melon away?
Even though there's a lot of damage, the basic structure is still intact.
With the heat of the impact, the Earth and the debris were both molten. And that molten state is the reason why the impact didn't leave a massive crater behind. The molten Earth reformed as a sphere and eventually cooled. So is there any kind of impact that can turn a planet into dust? Number 7, when worlds collide. Deep in space, 2 planets, one the size of Venus, the other Earth, are on a collision course. They're rocky planets, possibly even harboring life. Something in their solar system has pulled them out of their regular orbits, and instead of a glancing blow, they smash together in a head-on collision. Anyone standing on those planets would have witnessed a terrifying event.
You can imagine if you had a direct view of the planet moving toward us, that means the sky would quickly fill completely with this planet about to impact, and then it would be over like that. It would be such a rapid extinction of life that you probably wouldn't have time to think about it.
This isn't some fictional doomsday scenario. Some researchers think this massive blast rocked the cosmos within the last 1,000 years in a binary star system about 300 light-years away. It's known as BD plus 2307 in the constellation Aries.
It has a tremendous amount of dust in it, 1 million times more dust than in our solar system. We think that this dust may have been produced by the collision of two planets, roughly the size of the Earth and Venus, just head-on, whack, shattering each other, producing a tremendous amount of dust.
It takes enormous amounts of energy for two planets to pulverize each other into dust. Now, instead of hundreds of times the world's nuclear arsenal, we're talking millions of times or even billions of times that energy. With this even larger charge, we're not just going to break off a chunk of this melon, we're going to blow it to smithereens.
But as terrifying and destructive as planetary collisions can be, they're still much smaller than the different types of blasts that come from stars.
It's a whole new ballgame. The main reason is that there's a lot more mass in a star than any planet-sized object. And then there are all kinds of mechanisms that can take place involving nuclear fusion or various processes that involve gravitational collapse, which can drive a lot of energy as well.
One of these energetic blasts is number 6 on our list, magnetar flares. Magnetars are rapidly spinning neutron stars, which form when stars several times larger than our sun begin to die and collapse in upon themselves. Imagine if our 865,000-mile-wide sun suddenly compacted to the 12-mile length of the island of Manhattan. All of that matter is condensed into something so dense, it's estimated to be 10 billion times stronger than steel.
To give you an idea of how incredibly dense neutron star material is, if this cap was filled with neutron star stuff, it would weigh 100 billion tons on Earth. More than this hill, as much as an entire mountain.
The magnetar name comes from the fact that certain neutron stars, for reasons that are still unknown, have the strongest magnetic fields in the universe.
The magnetic field of a magnetar is exceptionally strong. It can be 1,000 trillion times as strong as Earth's magnetic field. That's fantastic.
The magnetic fields are so intense that if a magnetar suddenly appeared halfway between the Earth and the Moon, it would be strong enough to disrupt all of the electronic equipment on the planet, including stripping the information off every credit card on Earth. And the reason magnetar flares are so powerful is that the magnetic fields around certain areas of the star sometimes twist themselves so much that they can't twist anymore, and suddenly release like a spring.
The process is similar to a solar flare in that it's the magnetic field that's giving rise to the energy. It's the shaking and tangling and sometimes the reconnection of lines of force going in different directions that gives the energy that powers the flare.
But unlike planetary collisions, where kinetic energy dominates, magnetar flares shoot out most of their energy as electromagnetic radiation. In other words, light. And one magnetar flare in particular was strong enough to blind satellites orbiting Earth from 50,000 light-years away. The biggest blasts in the universe dwarf anything we can imagine on Earth. We're already billions of times beyond the entire nuclear arsenal of the world. Number 6 on our countdown are the flares that burst from incredibly magnetized neutron stars, known as magnetars. And one of the most powerful ever observed from Earth released as much energy in just over 1/10 of a second as our sun does in about 100,000 years. The blast in 2004 came from a magnetar known as SGR 1806-20 in the constellation Sagittarius. It's about 50,000 light years away from Earth on the far side of the Milky Way.
It was incredibly powerful. All that energy came in 1/10 of a second. It blasted the detectors and satellites that happened to be flying around up there. In fact, it was the brightest blast ever seen from an object outside our solar system. And yet, it was 50,000 light years away.
But what does brightness have to do with the power of a blast?
So I'm standing in a dark room here, and now I'm going to turn on a light bulb. How bright that light bulb appears to me depends on 2 factors. It depends on how intrinsically powerful or luminous the light bulb is, its wattage, how much energy it puts out per second, and it also depends on the distance of the light bulb from me. When I'm close to the light bulb, I see that the light bulb is bright. If I move a factor of 2 farther away, then in fact it looks a factor of 4 fainter. That's the inverse square law of light. The power of the light bulb has remained the same, but by being twice as far away, I get only 1/4 of the light reaching my face and my eyes. Astronomers measure the apparent brightness of the star or the explosion. They figure out its distance through some other technique, and from those 2 variables, they figure out the power or the luminosity of the source.
That light is released not just in visible wavelengths, but across the electromagnetic spectrum. And anytime researchers detect gamma rays, like they do in magnetar flares, they know it must be a big blast.
Gamma rays are a type of light, but a much more energetic light than we see with our eyes. So the spectrum of light that we're familiar with goes from very low energy and through the visible part of the spectrum, the light that we see, all the way out through X-rays into this extremely high energy component of light, which is called gamma rays.
Even a 1/10 of a second short gamma ray flare, like SGR 1806-20, would still be able to fry the Earth with radiation from many light years away, as long as the full force of the flare was aimed at Earth. But not all of the biggest blasts in the universe are over in a fraction of a second. Number 5, the 100-million-year blast. 2.6 billion light years away from Earth, a supermassive black hole, billions of times the mass of our sun, has been wreaking havoc in the center of a cluster of galaxies. Known as MSA 735, it's been shooting out 2 continuous jets of particles in opposite directions. Scientists believe the jets have been raging for the past 100 million years, punching 2 huge bubbles into the surrounding galaxies.
MSA 735 really is the prototypical example of a black hole blowing bubbles. What we're seeing here is giant cavities being evacuated by these powerful jets. They transport vast sums of energy down from the black hole out to huge distances, maybe about 1 million light years or so.
1 million light years is 10 times wider than our Milky Way galaxy, which means these jets are powerful enough to create 2 very big bubbles.
The total energy within these 2 bubbles is stupendous, far exceeding any other amount of concentrated energy that we know of in the universe. However, it must be remembered that the energy was released over 100 million years. That means that per unit of time, the total amount of energy released wasn't all that big.
Still, the jets are strong enough to shoot the particles out at millions of miles an hour, about a quarter of the speed of light. The jets and resulting bubbles only come from about 1% of the most massive black holes in the universe. That's because the forces near these monsters are so huge that instead of swallowing everything, they actually end up pushing some particles away.
It's important to emphasize that these giant explosions are not the explosion of the black hole itself, but rather an ejection of particles from near the black hole, the vicinity of the black hole. By colliding with one another, they can, in some cases, be ejected out of the vicinity of the black hole.
But how can this two-sided blast possibly keep going for 100 million years? It's all a matter of how much cosmic stuff is available, as planets and suns are stretched and ripped apart down to their very atoms and drawn towards the black hole.
So these jets that we've estimated have been going on for about 100 million years still have a huge amount of fuel available to them. That process can go on for an extremely long time, hundreds of millions of years.
Now, imagine taking a big chunk of that energy and releasing it in less than 2 seconds. That's what researchers believe happens in blast number 4, short gamma-ray bursts. Gamma-ray bursts are more concentrated than magnetar flares.
It's a concentrated beam of radiation, like a laser beam. It comes out as a narrow stream.
The gamma rays in the beams are also traveling much faster than the particles coming out of black hole jets.
The observations show that the energy is coming out in jets, moving at very close to the speed of light, 99.9999% the speed of light.
At that mind-bending speed, in just a few tenths of a second, short gamma-ray bursts can release as much energy as our sun does in millions of years. But for years, scientists couldn't figure out why some gamma-ray bursts were long, lasting many seconds or even minutes, while others were usually only a fraction of a second. Then, one burst in 2005 led researchers to an exciting new theory about incredibly dense neutron stars annihilating each other. The power of man-made atomic bombs is nothing compared to the galaxy-rattling explosions in the cosmos. As we continue counting down 10 of the biggest blasts in the universe, these cataclysmic events are now producing as much energy as our sun does in millions of years. Short gamma-ray bursts are number 4. For years, scientists have been confident of the source of long gamma-ray bursts, those that last over 2 seconds and sometimes erupt for many minutes. They come from galaxies with massive stars. And when certain massive stars die, they collapse and then explode, blasting out incredible amounts of energy as concentrated jets of gamma rays. But in 2005, detectors in space captured a powerful gamma-ray burst that only lasted for a fraction of a second.
This was very exciting because all the gamma-ray bursts we'd seen before were of the different variety, longer, coming from galaxies where massive stars were dying. This was something different. It was short, and it came from a region where no massive stars existed.
This burst came from a galaxy thought to have some incredibly dense neutron stars in binary pairs that orbit each other. And scientists believe that the only way to generate such a quick and powerful burst of gamma rays is if two neutron stars engage in a deadly dance, orbiting closer and closer, then finally crashing into each other. This is thought to be the moment when a black hole is born.
When the two neutron stars finally touch, one of the neutron stars gets shredded into a disk, and the thing that's left is too big to be a neutron star. There's no force in the universe that can hold up two neutron stars, so it collapses to a black hole.
The 2005 event, known as GRB 050509b, since it was the second burst to occur on May 9th of that year, was the first short gamma-ray burst whose location was pinned down. It didn't look very bright from Earth, but that's because it was an astounding 2.2 billion light-years away.
GRB 0509b lasted only about 40 milliseconds, but in that time, it released about as much energy as the sun will release in 100 million years.
But the power of colliding stars can't compete with the even larger amount of energy released when an entire star explodes from the inside out. Number 3, supernovas. When large stars die, they don't just fizzle out like our sun eventually will. They go out with a bang. There are actually several types, but the two main ways a supernova explosion happens is either when one star in a binary star system swallows part or all of its companion, or when a supermassive star collapses in on itself and ejects its outer shell in the process. Either way, a mind-boggling amount of energy is quickly released.
The energy of motion, the kinetic energy of the ejected material, can equal the total amount of energy that the sun will release over its entire 10 billion year lifetime.
The binary star type of supernova is similar to a hydrogen bomb, where runaway nuclear fusion leads to a massive explosion. These are known as Type 1a supernovas, and in 2003, one of these blasts flooded the cosmos with more light than an entire galaxy of stars combined.
It was over 20 billion times more luminous than the sun for about 2 weeks. And this all came from the explosion of something not much bigger than the moon, about 1.4 times the mass of the sun, from a thermonuclear explosion from fusion.
For the core collapse type of supernova, an incredible amount of power is generated when the outer shell slams down and gets an extra kick from the denser core of the star.
Imagine this ping pong ball represents that outer, lighter material of the star, whereas this superball represents the heavy inner core. You can see that the ping pong ball actually doesn't really bounce that much on its own, and there's the bounce of the superball. But what you'll see is that when I send them down together, the bounce of the superball back up will propel the ping pong ball much higher. And that's very much like what happens in the supernova, where you have the heavy inner core bouncing back out and meeting that lighter material and blowing it out.
In fact, one supernova explosion in 2005, known as SN 2005-AP, flashed brighter than all of the others for weeks on end. But it didn't do any damage to Earth because, luckily, it was also 4.7 billion light-years away. And like many of the other blasts on the top 10 list, supernovas don't just destroy.
A supernova is a little bit like a recycling center. There's a lot of material in those massive stars. It's anything from 8 times to over 100 times the mass of our sun. So there's a lot of material that's going to be processed in those stars, just like there's a lot of raw material here at the recycling center that's going to be processed.
The matter in the universe is dominated by light elements like hydrogen and helium. But the inside of a star about to go supernova is the main source of the various metals and other heavy elements we depend on for life.
Just like these materials are being sorted into different categories, the star starts to process heavier and heavier elements, starting with hydrogen, then helium, making heavier and heavier elements all the way up to iron when the fusion process stops. Later on in its life, when it becomes supernova, with the aid of the compression effects in the supernova, the star will make even heavier elements. Just as these materials are now packaged and processed and ready to leave the recycling center and go out into the world to be reused, the materials that were made in those stars that were then finally cooked and blown out into the universe by the supernova process, those will be reused as well. They may be used in other stars or perhaps other planets. The materials that we're made of here on Earth, the materials even in our bodies, those heavy elements were made in supernovae.
While supernovas are massive explosions themselves, they can also trigger secondary blasts with even more concentrated energy. Number 2, long gamma-ray bursts. The long gamma-ray burst comes out of the most powerful supernova explosions. They're as strong as the short gamma-ray bursts, but since they last much longer, anywhere from 2 seconds to nearly half an hour, they blast out much more energy overall.
The long gamma-ray bursts are completely different beasts compared to the short gamma-ray bursts. They're immensely more powerful, maybe up to around 10,000 times more powerful than the short duration bursts.
These concentrated jets of energy only come from supernova explosions involving stars 30 or more times the mass of our sun. And just like the short gamma-ray bursts, they're evidence of the birth of a black hole.
Long gamma-ray bursts are, in some sense, a variety of hyperenergetic supernova. The iron core collapses as before to a neutron star, but too much material falls down on it and it can't stay a neutron star. The temperature rises to 10 billion degrees. The luminosity in 1 cubic inch of this is as big as the sun. And this power can't flow out on the equator. It gets focused like in a shotgun blast out the rotational axis of the star.
So how much energy do the most powerful long gamma-ray bursts release compared to our sun? The answer is shocking. We're at number 2 in our countdown of the biggest blasts in the universe, long gamma-ray bursts. They're the most powerful concentrated beams of energy in the universe. They release many times more energy in a matter of seconds or minutes than our sun will produce in its entire 10 billion year lifespan. The key to their devastating power is focusing that energy in a narrow area. A firearms expert illustrates the point with 2 different shotguns. First, a shorter gun, where the shot spreads out quickly after leaving the barrel, unlike a gamma-ray burst.
As you can see, there's some damage to the melon, but not that much because the shot was spread out and only some of it hit the target.
Now our firearms expert is switching to a longer barrel that keeps the shot concentrated in a tighter pattern as it goes downrange. The same effect as a gamma-ray burst.
Concentrating the shot can be devastating. It's a good thing for us that most gamma-ray bursts are millions or billions of light years away from Earth and are pointed in the other direction.
It's believed that these concentrated jets shoot out when massive stars collapse into black holes. And in 2008, scientists detected one of the strongest gamma-ray bursts on record, known as GRB 080916C. It lasted an incredible 23 minutes.
This GRB was one of the most exciting blasts ever seen because the total power inferred from the observed brightness and the distance of the blast exceeded that of any other known GRB up to that time. Moreover, we can tell that energetic particles were blasted out along two jets at 99.9999% of the speed of light. GRBs are so powerful along the beam of particles and radiation that even ones that are thousands of light years away, but pointing at us, could destroy much of the life on Earth.
But if long gamma-ray bursts are the most powerful explosions in the universe, then how could they be number 2 on our list? Because the top spot goes to something that didn't happen within the universe, but happened when the universe itself was formed. Number 1, the Big Bang. This mother of all blasts is technically an expansion and not an explosion, since it was not a blast within a defined area.
It wasn't an explosion that happened somewhere in space. It's all of space. It's the actual fabric of space-time itself coming into existence. So in the concept of a biggest blast, it's as big as it gets. It was the whole universe blasting into existence.
And the speed and temperatures of the Big Bang dwarf anything that happened inside the universe once it was formed.
Those temperatures are beyond anything we can imagine. There are trillions of degrees if you measured it in usual units. So compared to any explosion, say here on Earth or a star or what have you, this is well beyond that.
Researchers believe that theoretically, they can go back so close to the moment the Big Bang happened that a fraction of a second doesn't come anywhere close to doing the timescale justice.
The bang of the Big Bang is a time in the early universe known as inflation. The size of the universe went whoosh. It just expanded so quickly, doubled in size many times over a very, very short interval of time. This incredible inflationary exponential state of expansion lasted only a tiny fraction of a second. A millionth of 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 a second.
During this early expansion, it seemed as if things were moving faster than Einstein's universal speed limit, the speed of light.
In fact, it expanded so quickly that it was faster than the speed of light. That's okay. That doesn't violate Einstein's theory of relativity. Space itself can expand faster than the speed of light. No particle can travel through space faster than the speed of light, but space itself can and does expand faster than the speed of light.
And the Big Bang is the largest reminder of all that the biggest blasts in the universe, these sudden releases of energy, do much more than destroy.
The creation of our universe, the creation of the sunshine that comes out of stars, and the creation of our own moon all came from this tremendous liberation of energy all at once. So there's a very intimate link between matter manifested in one way and then being destroyed and then re-emerging in a new way. And, you know, here on Earth, it re-emerged as us.
And as the universe evolves, its biggest blasts will continue to be both the destroyer of worlds and the creators of new possibilities.